Hi guys, I was asked to make a video and do some clarification about the derivatives of exponential functions. So I'm going to make two different videos here. I'm going to do a first video talking kind of about the general shape of the derivatives of different functions and how we come up with the derivative of exponential functions, and also that special number e, or Euler's number, and the natural logarithm. And then I'll do another video where I do some examples of the different derivatives of exponential functions and logarithmic functions and how we can calculate those. So the first thing that I really wish we were in class for me to be able to do this, but I think it's important to kind of understand and recognize that you can tell things about the derivative of a function from looking at the base function. So for instance, I'm just going to draw a really simple parabola here. And I want you to think about what the derivative of that function would be. So if we have f at x, which is just y equals x squared, or f at x equals x squared, remember what the derivative means. The derivative is an equation that represents the slope of the tangent at any point on the function. So that's really, really important. I want you guys to understand what the derivative means, that we're not just coming up with this other equation or other graph, but that new function is actually a description of what's happening to the tangent of the original function for all the different values of x. So if we just kind of very, very roughly look at what the slopes of the tangents would be doing on this graph, we know that when, say, we have negative numbers, that the slope of the tangent is going to be negative. It's pretty big negative there, pretty steep negative tangent. As the negative numbers get larger or closer into zero, we still have a negative tangent, but they're getting to be smaller negative numbers. So this one is much steeper negative, and then it gets into smaller kind of on the number line negative. We see here at the vertex, we would know that that is a slope of 0 because it's a turning point. So if I kind of graph those values, and again, not with any kind of scale, but just to see what the shape of this would be, I have big negative numbers, small negatives, and then 0. So I've got some kind of big negative number, then a small negative number for my y value that would match up with the same x values on this original one, and then it's at 0. And then as I look into the positive side of the graph, I have a smaller positive slope, and then progressively getting to be bigger positive slopes. And the further out you go on the parabola, the bigger the positive slope would be. So somewhere over here, I would have a small positive slope and then bigger positive slopes. So we're going to get generally a linear function. For the parabola that's opening upwards, we're going to have a linear function that's opening, has a positive slope. We can see kind of other examples, and I really think that this is a good exercise to kind of go through and think about what the shape of the derivative of different functions might be. So here I have a general kind of cubic graph, and I'm very intentionally not putting any scale on this, but we would see, what would we know about the derivative of this function? First of all, we would know that at these turning points, so here and here, we've got a slope of 0. So I'm going to, for this one, just do a sketch of the derivative on the same axis. So here we would have a slope of 0 and a slope of 0. Now for all of the points on this side of the function, like after this turning point, we're going to start off with small positive slopes. So the tangent is small positive here and getting to be steeper, getting to be bigger positive tangent. So after this turning point, or the 0, it's increasing in the positive direction. So up like that, okay? And on this piece, it's kind of the opposite, right? We'll have positive tangents for all of these pieces on this part of the graph. And close into the turning point, they're going to be pretty small positive, but then they're going to get really big positive slopes out here. It's going to be steeper and steeper positive. So kind of the same picture again out here. So again, I'm just going to kind of label my black pen with f at x, and the one in pink is going to be the graph of the derivative. We can then look between the two turning points. It starts off as small negative, so it's decreasing function. You've got a bit of a negative slope there. It gets to be bigger and bigger negative, but then it starts to level out to a smaller negative number close into the other one. So it goes from small negatives to bigger negatives, and then it starts going up back into smaller negatives to the other turning point. So here we see graphically what you guys already know from the power rule, that the derivative of a cubic function is a quadratic. But I want you to see the connection there between what the graph is doing, a graph of the function, and how the tangent line is changing and why that's true. So another function that we could look at is, say, y equals 1 over x, so a rational function. So something like that. If this is my original function, what do we see about the slopes of the tangents for all of these? So for these points, we've got little negatives getting to be bigger negatives, and as we get into the asymptote, it gets really big negative slopes. The other piece is actually going to also be all negative slopes. So you've got really big negatives, really smaller negatives, but it's never going to have a positive slope. So that means that the graph of the derivative of this function will never be in a positive y value. All of the slope is negative. The slope of the tangent is always negative for every point on that function. So that means that the graph of the derivative will always be in the negatives. And the graph of this one, really big negatives close in to the asymptote. So really big negative close into the asymptote. And then getting close to, especially if you go way out here, we're getting close to a slope of 0. It never hits a turning point. It never gets to 0, but that's going to get closer and closer, and that's going to be a horizontal asymptote on the graph of this derivative. So it's a good idea to kind of take a look through and think about what the graphs of derivatives of functions that you know, what the graphs of their derivatives would look like by analyzing what the slope of the tangent is. Now we're going to come to an exponential function. So this is kind of where we're going with that. That if we had, let's say, y equals a to the exponent x, we see for sure that this is always going to have a positive slope. All of the points on this graph is always increasing, so the slope of the tangent is positive for every x value. If we take a little bit more look at it, the slope of the tangent is very small positives on the left-hand side, and it's gradually increasing to get bigger and bigger positives. So the slope of the function is always positive. It starts out low in the negative x values and increases in the positive x values. So hopefully you guys can see that that means that this is going to follow some similar curve. Oh, I said y equals here. I should have said f of x because I've got f prime. So that the derivative of this function follows a very similar curve and very similar shape to the actual graph of the function. So that's a special thing about exponential functions in general. And there's one exponential function that has a base of that really important irrational number E, or Euler's number, and the property of that number is that if the base of an exponential function is e, then the derivative is exactly the value of the function itself. Now, that's not going to be true for most exponential functions, but you can see that for any exponential function, any base a, the derivative function is actually a scalar multiple of the function itself. So it follows the same shape for sure, but it just has a stretch or compression factor. The function y equals e to the x, or f at x, equals e to the x, and e is just a number, it's just a base of about 2.7, means that the derivative of that function is also e to the x. And that's the only function where that's true, where the function itself and the derivative are exactly the same thing.